Hello everyone, and welcome to the ultimate guide to NumPy arrays, where NumPy is a popular Python library that deals with numbers, and arrays are a special data structure that NumPy offers. So in this tutorial, we will learn how to create arrays, how to sort them, reshape them, adjust their values, and we will also see exactly why arrays are so much better than lists. Well, at least when it comes to numeric data. Now, if you're new to this channel, welcome to Python Simplified, where I, Maria, share helpful programming tutorials, which will take your Python skills to the next level. So what exactly are we waiting for? Let's start coding. And we will begin by installing NumPy with pip install NumPy. Now, if you're using Anaconda, I'm including the equivalent command in the description. But because this time I'm using WayScript, I already have this built-in terminal, so Anaconda is not really necessary in my case. Cool. Now, once we have successfully installed NumPy, we can then go ahead and import it with import NumPy as np. And now we can use it to generate our special data structure, which is officially called an n-dimensional array. But we will just call it array to save some time. Now, one way we can create a new array is with the np.arange function. Now let's see what happens if we pass the number 8 into it. Curious. Let's assign it to my_array, and let's print it right below. So print my array. And actually, let's also print the data type of this object with print type my array. Okay, let's save everything and let's give it a quick run. And beautiful, we see that we are dealing with a NumPy ND_array object, which consists of 8 different digits organized in a sequence where the first digit is 0 and the last digit is 7. So in this example, the number 8 represents something called a stop value. So once we reach this value, we stop counting and we do not include it inside the array. Now by default, we always start counting from 0. But what if we don't want to start counting from 0? What if we want to count from 1? Well, in this case, we will simply specify 2 arguments inside the arange function. So let's just copy it, and we will keep reassigning new values to it so we don't lose the progress. So in the case of starting to count from 1, the first argument we specify is the start value, so 1, and the last argument is the stop value, so 8. Okay, let's save it, and let's see how it looks like. And beautiful, we are officially counting from 1. Okay. But what if we don't want to include all the digits from 1 to 8? What if we want to only include the odd digits, so only every second digit? Well, in that case, we will specify 3 arguments inside my array. So we will just copy this line of code, where the first argument remains the start, the second argument remains the stop, and the last argument represents something called a step. So in our case, we would like to jump 2 numbers at a time, and that's why we specified 2. If we rerun this code, we are now only fetching the odd digits. Cool. Now, we are not exactly limited to whole numbers inside this arange function. So we could have realistically went for a half in terms of step. Okay, let's save it. And beautiful, now we are working with floating point numbers as well. And actually, there's nothing that prevents us from specifying negative digits as well. So let's say -1, and let's go for 9.25 in terms of the stop value. And in this case, not only we are working with floating point numbers, but we are also working with negative ones. So we can use arange to generate all kinds of sequences. But that's not the only way. Alternatively, we can also generate arrays from lists. To do this, we will use the np.array function, to which we will pass a list of 1, 2, and 3. We can now assign it to from_list. Let's quickly print it below. And we have successfully converted our list into an array. But why would we want to do something like this? Arrays and lists, they kind of look the same and they kind of have the same purpose. So what's the point in converting from one to another? The main point is memory efficiency. So whenever we are dealing with lists, we can store all kinds of data types inside. We can store integers alongside Boolean and strings and even other lists and dictionaries. So we are very flexible in terms of the size of data we can store in a list. But the only problem is this flexibility wastes a lot of resources. So for example, a Boolean takes up much less space than a string, because a Boolean can be either of two values. It's either true or false. It's either 1 or 0. So we are always dealing with two options. While strings, they can be either of 26 lowercase characters, 26 uppercase characters, 10 digits, alongside all kinds of punctuation symbols. So we are dealing with well above 70 different options. And this is just for a single character. I'm not even talking about a word or, God forbid, a sentence. So the fact that we can store both of these data types on the exact same list is just madness. Now this, while NumPy arrays are meant to store a very specific data type. And I don't just mean it in terms of integers versus floats. I mean it in terms of the number of bits that those integers and floats take up. So for example, let's print the data type of one of our array items. Okay, so we will just do this with print type from list, and we will go for the very first item, which is given by index 0. Let's see how it looks like. Okay, so we are dealing with an integer that takes up 64 bits. So do we really need 64 bits to convey 1, 2, and 3? Let's check. And the way to do this is to convert those decimal numbers into binary numbers. And if you guys are not sure how to do this, I have an amazing video which will get you up to speed. So check it out and you'll become an expert right after. Okay? Now, whenever we convert 1 from decimal to binary, we get 1. Whenever we convert 2, we get 1, 0, and 3 is 1, 1. So realistically, our biggest number only takes up 2 bits. So why do we need 64 of them? We don't. And we can actually solve this problem very easily. We just specify a data type argument inside our NumPy functions. And I mean it both in terms of the array and the arange function. So for example, we will just add a comma following dtype, as in data type, and we will set it to a very small integer with np.int 8, where 8 bits is a byte, but I don't know if it matters. It's just for general knowledge. And now if we rerun this code, we officially consume less memory than before. So does it mean that our code is now processed more efficiently? Not necessarily. So just because we take up less space, it doesn't mean that it results in less time. It all depends on your hardware and on your operating system. And if you guys want to find out more about it, definitely leave me a comment below. We can dedicate an entire video to hardware and bits and all those technical stuff. Okay, now so far we've learned about one-dimensional arrays, where all the items are placed in a single line. But what if we'd like our data to have rows and columns? Now, one solution is to pass a two-dimensional list into our array function. So for example, let's just copy our from list command from earlier, and we will then wrap the original list in another set of square brackets, to which we will pass an additional list of 4, 5, and 6. And once we do that, we can then print from list, and let's have a quick look. And beautiful! We are now dealing with a two-dimensional array because we are dealing with multiple rows of data. Now, alternatively, we can also do it the arange way. So once again, we will start with np.array, but this time we will pass a tuple or a list into it, it's all up to you, with np.arange, to which we will pass a start value of 0, a stop value of 8, and we will step by 2. And then right next to it, we will pass another np.arange function, and this time we will pass 1 as a start, 8 as a stop, and 2 as a step. And we can then assign it, let's call it array underscore 2D. And of course, let's print it right below. And beautiful! Once again, we are dealing with multiple rows of data, where the first row stores all the even digits and the last row stores all the odd digits. Now we can also verify that it's a two-dimensional array by printing its shape. So we will just simply add .shape after the name of the array, and let's actually turn it into a more informative print statement. So we will say 2D shape. And just for comparison, we will also print a one-dimensional shape, which we have done earlier. And let's go for our my_array variable. Let's save everything and let's have a quick look. Awesome. We see that the one-dimensional shape only tracks the number of columns. So shape only returns a single value, while the two-dimensional shape tracks both the rows, which in our case we have 2 of them, and the columns, where we have 4. Now, okay, but what if we don't like this shape anymore? What if we want to change it somewhere along the way? Well, we can just simply use the reshape method. So we will type array 2d.reshape, and let's try to flip our rows and columns. So we will set it to 4 rows and 2 columns. Okay, which is the exact opposite of what we currently have. And actually, let's reassign it back to array 2D. And also, let's have a look in this array. We will just comment out the one-dimensional shape, and we will print the array itself. So array 2D. Aha! Look at that! We are dealing with a completely different shape now, and we have successfully flipped between the number of rows and the number of columns. Now, one thing I should mention is we are not limited to the exact same dimensions of the original array. So, for example, we could have specified a one-dimensional shape here. So let's go for 8. Okay, let's resave everything and let's see the effects on our code. And there you go, we are getting a completely flattened array. Or alternatively, we could have specified a 3-dimensional shape here. So for example, we could have went for 2 channels, we could have specified a single row on each channel and 4 columns for each. Let's save it, let's see how this would look like. And beautiful, shape now returns 3 arguments, and we are once again separating our data into odd digits and even digits. Now we could have also specified a 2 by 2 by 2 shape here, or anything else that perfectly divides 8, okay? Because 8 is the total length of the original array. So we are quite limited with the choices of shape here. Now sometimes we don't know in advance which values to store inside the array. So very often we start with an empty array and we fill it with data as we go. Now NumPy has 3 different functions to create empty arrays, where the first one is np.zeros, to which we will pass some kind of a shape. So let's go for 2 by 2 and let's assign it to empty_array. Now we can then print it right below, and let's have a quick look. And perfect! We get a data structure in the exact same shape we have specified, where all its values are equal to 0. Now alternatively, we could have used a very similar function, which is called np.once. And as you may guess, instead of filling our entire data structure with zeros, we are filling it with ones. Now, the last function I'll show you is definitely not my favorite one, but it exists, so I'll share it anyways. This one is called np.empty. Now, if we run this code, we see very similar results to np.zero. So does it mean it's the same? No, because if we change the shape, we pass into this function and we rerun this code, we are getting completely different values in return. So empty returns random values. And if you're a big fan of surprises, sure, you may find it handy. But personally, I wouldn't use this function. And the main reason is because it returns unexpected results, which is something that I don't like to see in my data, but that's just me. Another type of array, which you may find handy, is given by np.I. Now let's see what happens if we pass the number 3 into this function. So let's quickly assign it to I array. Let's print it below. And we get a data structure with 3 different rows and 3 different columns, where the main diagonal is entirely filled with ones, while everything else is filled with zeros. Cool. Now, we are not exactly limited to the main diagonal. We can select any other one by specifying a k value. So we will simply add a comma followed by k equals, let's say, -1. And once we do that, we are selecting one diagonal below. And we are filling it with ones, of course. Now, if we do the same, but with 1 instead of -1, we are selecting one diagonal above, and so on. Cool. But is there a way for us to manipulate some of the values of this array? So for example, what if we'd like to replace all the zeros with 2s? Well, in that case, we will just simply use a filtering command. So we will type I_array. We will then open a set of square brackets where we will only select the I array values that are equal to 0. And once we have filtered the rest of the result, we will then assign it to 2. Now let's save this code. And beautiful! All our zeros are now 2s. But we are not exactly limited to the equality operator only. We could have selected any other operator. So for example, IArray, where we open a filtering command where we'd like to keep all the IArray values that are smaller than 2. And if we encounter such values, we will then set them to 9. Let's see if it worked. And beautiful, our 1s are now equal to 9s. Now, what happens if we'd like to filter entire rows or entire columns? So for example, what if we'd like our first row to be, entirely filled with 3s? And that's even easier to do than the previous commands I showed you. We will simply type IArray in the index of 0, which is how we select the first row, and we will set it to 3. That's it. Okay, if we save this code and rerun it, our first row is now made of 3s. Now, similarly, we can select the first 2 rows simply by selecting all the rows given by a colon up until row number 2. Okay, and once we specify that and we rerun our code, our first 2 rows are now being selected and modified to 3. Okay, but what if we'd like to select the last 2 rows? Well, in that case, we will simply start counting from the first row. So we will skip row 0, and we will then include all the rows, until the very end. Cool, let's save it. Let's see if it worked. Awesome. So whenever you see a colon inside slicing commands, just imagine it as the word all. Okay? Cool. Now, what if we'd like to select columns? So for example, let's say we'd like our first column to be entirely filled with 4s. Well, in that case, we will type IArray. We will open a slicing command where we will select all the rows first. We will then add a comma, and then we will indicate the columns. Now, in our case, we'd like to select the first column, so we will type 0. Okay, we will then set it to 4. And let's see if it worked. And beautiful, our first column is now consisting of 4s. Now, in addition, we also have the option to start selecting from the end of the array rather than from the start. So for example, if I'd like to set our last column to 4s, I can simply specify -1, which represents the last column. So let's save it. And there you go. We are now selecting the last one. Now we can keep customizing this further. So for example, let's select the last 2 rows and I guess the first 2 columns. Let's do it. And beautiful. Now we can be very specific with our region of interest. Awesome. Now how can we sort arrays? Well, we'll just simply type np.sort, to which we will pass some kind of an array. Let's say IArray, and let's assign this expression to sorted array, and let's quickly give it a print. Now I actually want to compare it with the original array, so I'll print it as well right above, and I'll just add an end of line operator with \n, end of line character, sorry, and this will give us a nice gap between the print statements. Let's save everything. And beautiful! While our original array is quite messy, our sorted array organizes each row in a sequence, where the first item is the smallest number and the last item is the largest number. And this is consistent across all the rows. But we are not limited to sorting by rows. We can also sort by columns. And to do this, we will specify an additional argument of axis. And we will set it to 0, where 0 indicates columns and -1, which is the default, indicates rows. Now let's give it a run and let's see the effect. Beautiful! Now we are sorting by the column. Awesome. So each column starts from the smallest number and it ends in the largest number, while our rows are completely messy. But that's okay, because it's an either or kind of situation. Now, another cool thing we can do with sorting, we can actually be very specific in terms of the algorithm we select. So for example, by default, we are working with quicksort, but we are not limited to quicksort only. We can actually specify a kind of algorithm. And for example, let's set it to merge sort. Let's save it and let's rerun our code. Now, we don't really see any changes and we don't really feel them in terms of time because we are working with a very small array. And in addition, we can also set it to heap sort, for example. And once again, we're not really going to feel it. But sometimes we are dealing with very complex data structures. These could be huge matrices with hundreds of dimensions and channels and thousands of rows and columns. And in these type of situations, different sorting algorithms may result in faster calculations. Even though very often quicksort will be the best solution, but it's a very good detail to keep in mind. And the last thing I'll show you today is how to make copies of arrays. Now, NumPy has two different methods to do so. The first one is called view, where we specify the name of the array, so let's say sorted array, followed by a .view method. Now we can assign this to my_view. Another method is the copy method, where we once again specify the name of the array, followed by .copy, and then an empty set of round brackets. We can then assign it to my_copy. But what's the difference between the two? Why do we need both? And the difference is one of them affects the original array while the other one doesn't. So what do I mean by affects? So for example, let's take my view and let's assign all its values to 4. We can do this with my view. We will simply select all the rows and we will assign them to 4. Now, when we do this, we will then print my view followed by an end of the line character, and we will then also print sorted array, which is the original one we made a copy of. Are you guys ready? Let's see what happens. Cool! And we see that not only we have modified the view, which is the copy, but we have also modified the original array, which is sometimes a good thing and sometimes a bad thing. And that's why we have this distinction between both copies. Now, if we try to do the same thing with my copy, okay, let's rerun everything. See, it doesn't work the same way with my copy. So yeah, we made the changes to my copy, but the original array was untouched. Now, another important detail I should mention, that even if we change the shape of my view, it doesn't affect the original array, only if we change the values within it. So for example, I could have said my view equals my view dot reshaped. And let's select some kind of a weird shape of 3 by 3 by 1, whatever. And if we try to print the copied array and the original array right below, ooh, reshape, not reshaped. Okay, and once we do that, we can see that my view was definitely affected. This is not a familiar shape. While the sorted array knows nothing of this change. And perfect! Now we know exactly how to work with arrays. In the next tutorial, we will learn about the things we can do with them. So we will talk about the arithmetic operations, about the methods and the tricks that NumPy has to offer. Now, if you enjoyed this tutorial, please give it a like. If you have anything to say, please leave me a comment. If you'd like to be extra awesome, you can always share this tutorial with the world, and you can always subscribe to my channel and turn on the notification bell. I'll see you guys very soon, so bye bye for now.